Hi again, everybody. So today is day 2. We're going to be talking about evaluating limits algebraically. Yesterday, we introduced the idea of a limit. We saw a bunch of different kinds of limits, left-hand limits, right-hand limits, two-sided limits, and we saw, or you should have seen, if you did the reading in the worksheet, that limits can have the value positive infinity or negative infinity. That's also possible. So we saw quite a lot of limits yesterday, and they were all in the context of graphs. And today we're going to be taking another look at limits, except we're going to be evaluating, that is, finding limits without a graph, which requires a completely different approach. Today's lesson is a lot more algebraically involved than yesterday's lesson, so be prepared for that. What I do want to do first, though, is go over some of the homework from yesterday. So some of the exercises from the first day. So I'm going to share my screen, and we'll just take a look at some of these problems. So it's not what I wanted. There we are. So, so hopefully you saw from this example here that you can have a function whose value, which has an infinite limit, right? So this function here, as x approaches c from the left, you can see that the value of the function is getting larger and larger, or actually it's becoming a more and more large negative number. So we would say that the left-hand limit is negative infinity for a function like this. And as x approaches c, you can see that the value, as x approaches c from the right, you can see that the value is getting larger and larger in the positive direction. We would say there that the right-hand limit is positive infinity. Now, I want to make a clarification about, sometimes students get really hung up on whether they're supposed to say that the limit doesn't exist, or is it infinity, or what's going on with that. And I want to make sure that you guys understand. We encourage you in situations like these to write dne and then in parentheses positive infinity, like we would say here. So this is the limit as x approaches c from the right, and as you can see, we're claiming that the limit as x approaches c from the right in this case is dne, which means does not exist, and then positive infinity. So what's the deal with dne positive infinity? Why do we say both? So the thing is, this limit doesn't exist. First of all, let's be clear about why that is. A limit only exists if the value of the function is getting closer and closer to a number. All right. This function, you can say that this function is getting closer and closer to infinity, and that's true, but infinity is not a number. Okay, so as x approaches c from the right, this function is, its value is not getting closer and closer to a number. Rather, it's just getting larger and larger. And so because it's not getting closer and closer to a number, we say that the limit doesn't exist. Now, why do we write then in parentheses infinity? Because we want to emphasize that this function's right-hand limit doesn't exist in a particular way, right? It's failing to exist in the particular fashion that the value of the function gets larger and larger and larger without any kind of limit. And there are, in fact, lots of other ways that limits can fail to exist, right? They don't have to get larger and larger and larger in order to fail to exist. There are other ways that it can happen. So by putting in parentheses, what we're really saying is this limit doesn't exist because it's not getting closer and closer to a number. And specifically, it fails to exist because the value of the function is just getting larger and larger and larger and not approaching any particular value. So the parentheses are really saying, in parentheses, here's why it doesn't exist, or here's the particular way in which it doesn't exist. So that's why we say dne and then in parentheses, either positive or negative infinity. Now, I want to go over exercise 4. This is a tough one. We're asking you to sketch a graph, and you're trying to sketch a graph of one function, a single function, which simultaneously has all of these properties, okay? And how are you supposed to handle something like this? here's the strategy. You should really try to draw the smallest amount necessary in order to meet each of these conditions, okay? And just focus on one condition at a time, okay? And just draw a little bit of the graph to make sure that that condition is satisfied, and then move on to the next one, and then connect all the pieces at the end. So that's what we're going to do. So let's take a look at this first condition here. We have the limit as x approaches 0 from the left should be equal to 2. So what is that saying? That's saying that whatever the graph of this function looks like, as you get closer and closer to 0 from the left, the value of the function should be approaching 2. So that could happen in all kinds of different ways. That could happen, for example, like this, right? That would certainly be an example of, as the function gets closer and closer to 0 from the left, the function is approaching 2. But it's certainly not the only way that it could happen. Certainly, like, I could go like this, and that would also meet that condition, right? That graph, or I could even go like this. Okay, all of those options would meet this condition that as x approaches 0 from the left, the value of the function approaches 2. So, there's lots of different, ways of doing this problem. I'm just going to go like this for right now. Okay, and we'll see if, and I think that'll be good enough. Okay, and notice that I didn't draw much of the graph, right? Like, I didn't draw anything out here, over to the left. I only drew the minimum that I needed to satisfy this condition, okay? And that's basically because there's a lot of other conditions happening, and I don't want to, like, contradict any of them, if that makes sense. Like, I don't want to get ahead of myself and draw something that contradicts one of the other requirements. So I'm just drawing the minimum that I need. So let's go on to property number 2. It says the limit as x approaches 0 from the right should be equal to -1. Again, lots of ways of doing that, but you could do something like this. Oops, I think I went a little too far there. Something like that, right? As x approaches 0 from the right, the value of the function is approaching -1. And now this one here, f of 0 is equal to 1. So that's saying that the value of the function at 0 is equal to 1. So what I need to do is that, I really need to make sure that, so f of 0 equals 1. That means I need a full circle right here. I need a full circle right here. And now the value of the function at 0 will be equal to 1. But if you think about it, that actually requires that I do some other things here and here. Because if I gave you this graph, let's say I gave you this graph right here that I've drawn, and I asked you, just based on this graph alone, what is the value of the function at 0? There's kind of 3 different answers you could give me. You could say, well, it's 1 because the graph is sitting right here. You could also say maybe it's 2 because the graph also seems to be right here. And you could also argue that maybe the value of the function is -1 because the graph is down here. That's really not allowed. That's bad news. Remember that functions are supposed to have only one output for every input, right? Like, if you input 0, you should be getting just one number back. So, like, this graph needs to be clarified to make it so that it's clear that the output is 1 and not anything else. And the way that we do that is we have to put empty circles, right? We have to put empty circles here, and also down here at -1. Okay, with the 2 empty circles, we're making it very clear that the value of the function at 0 is 1 and not any of these other values. All right, so what else do we need? We need the limit as x approaches 2 from the left is equal to -infinity. Okay, so that's saying that as you get close to 2 from the left, the function needs to be going down, down, down to -infinity. So, it just needs to be going way down to -infinity like this. Maybe draw a little arrow to just kind of indicate that it's doing that. Okay. And then as x approaches 2 from the right, the function's supposed to be going to positive infinity, so maybe like this. Again, there's lots of ways that you could do this. It could be looking like this, or, this piece could be down here. Like, it doesn't really matter as long as the value of the function is going to positive infinity as you get really close to 2 on the right. And then finally, it says the only discontinuities of f occur at 0 and 2. Now, why do I say that? Basically, because when students do these problems, what they tend to do is they draw like a bunch of disconnected pieces, which is exactly what I've drawn here. You can see that there are all these disconnected pieces. Like there's this piece right here, and then there's like a big gap, and then there's like a piece down here. And what we're trying to tell you with this last property is that we really only want you to be introducing discontinuities as necessary. Like, we don't want a bunch of different pieces. We want you to connect it as much as you can, so long as the function is still a function. That means it passes the vertical line test. Let me just be clear about what that means. If I connected this piece here like this to this piece down here, that would actually be failing the vertical line test. If you remember the vertical line test, it says a function has to have the property that any vertical line crosses the graph only once. And you can see that, I could draw a vertical line right here that would cross the graph more than once. So this graph would fail the vertical line test. In other words, this graph wouldn't be a function. Okay, so connecting these two pieces in that way is not allowed. So how could we, connect them? I mean, I think that, we just need to connect them so that, just sort of simply like this, and that's going to be sufficient right there. Okay. Now, as far as, what the graph is doing after this, it doesn't really matter. I mean, we're given no instructions about what the graph is doing as you go off to the left. So you can just do something like this. There's lots of different options, but as long as you're not introducing any additional continuities. And likewise over here, we don't really know what's going on with the graph over here. It doesn't really matter as long as it's, passing the vertical line test. It should be good to go. So that is certainly one option for exercise number 4. I'm going to start exercise number 5. Although I will say that 5 is pretty intense. There's kind of a lot. So let's see. So limit as x approaches -7 from the right should be positive infinity. So as I approach -7 from the right, the graph needs to be going up to positive infinity like that. As x approaches -5 from the left, the graph needs to be going to negative infinity. So as I approach -5 from the left, it should be going down to negative infinity like that. As x approaches -5 from the right, I want the function to approach 2. Okay, so here's 2 right here. So as I approach -5 from the right, I'm going to have it approach 2 like that. That's fine. Here's a tricky one. The limit as x approaches -3, that's the two-sided limit, exists, but f is not continuous at -3. So what's going on there? You have to think about that. If this two-handed limit exists, that means what? What's required for the two-handed limit to exist? It's that the left and right-hand limits have to be the same, right? So what we're telling you there is that the left and right-hand limits as you approach -3 have to be the same. But if you just went like this, that would not be acceptable because that would make the function continuous at -3, right? There's just a continuous curve there. So we want the two limits to go to the same value from either side, and yet somehow the function needs to be not continuous at -3. So how can you do that? A couple ways. One way certainly would be to have a hole at -3. So it could be something like this. Make a little hole at -3 and then go on. And as you can see, as you approach from the left and the right, you're getting the same value, whatever that value is. Looks like maybe 0.3 or something. And yet the function is not continuous at -3 because there's a hole. Okay. All right. What else? Number 5. And again, notice that I'm drawing very little. I'm only drawing like very locally just to make the graph match the condition that I'm given. I'm not like drawing graphs way over here because I know that there's going to be other requirements over here and I want to make sure I don't contradict them. So moving on to number 5, limit as x approaches 0, that's the two-handed limit, is defined. And f of 0 is defined, but f is not continuous at 0. Very similar to the last problem. So the fact that this thing is defined, you know, being defined and existing, same thing. The fact that that guy's defined means that the left and right hand limits need to be going to the same value. So it could be something like this, right? But we want it to be not continuous at 0. So I can't just have a smooth curve. Like there needs to be some kind of a gap here, right? There needs to be some kind of a gap, you know, but as long as it's going to the same value from either side, that should be good to go. All right. And as we can see, but notice this other requirement, f of 0 needs to be defined. Right now it's not, because all I have is an empty circle. Right now, this function doesn't have a value at 0. So I need to give it a value. I can give it any value I want. As long as I don't put the value right here, which would make it a continuous like curve through that point. And I could put it up here at 2, just put a full dot up here at 2. That would do the job, right? So in that circumstance, you can see that this matches the conditions, right? The function's defined at 0, it's equal to 2, and the two-handed limit exists, but it's not continuous, as you can see, there's a gap. 6, the limit as x approaches 2 is undefined. That's the two-handed limit. There's lots of ways of doing that. We just need to make sure that, you know, in order for the two-handed limit to be undefined, the left and right hand limits have to be going to different values. So very easy to do that. I just need to maybe do something like this, have a hole, and then just something like this. And as you can see, as you approach from the left and the right, you're getting 2 different values at 2, so the two-handed limit doesn't exist. F of 3 is equal to -2. Ooh, okay. That requires kind of a sharp drop there. I feel like I might want to move this down. Let me actually redraw this. Let's do this. So empty dot here and a line right here. I'll put a full dot there. Okay, so that's going to make sure that number 6 is still satisfied, right? The two-handed limit at 2 is undefined because you're approaching 2 different values from either side. But also f of 3 is equal to -2. As you can see, I've got that full black dot there. Okay, limit as x approaches 4 from the left is equal to f of 4, but f is not continuous at 4. What this is saying is that, you know, whatever value you approach 4 from the left is the same as the value of the function at 4. So I just need to put a full black dot here. But then it says the function, so as you can see, that makes it so that the left-hand limit is equal to the value of the function at 4. They're the same thing, they're both -1. But I need to make it so that the function is not continuous at 4, which means I need some kind of a jump from the right. So something like that. Right now, the function is not continuous at 4. There's a jump. Limit as x approaches 7 from the left is positive infinity. So that could be, that's pretty easy to do. Just got to do something like this. Okay. And then finally, the only discontinuities of f occur at -7, -5, -3, 0, 2, 4, and 7. Those are the places that basically must have discontinuities because of the earlier conditions that we imposed. But there's a lot of pieces here that can still be connected. Like, as you can see, it looks like I've got a discontinuity at -6, and I'm not supposed to have one. That's okay. I just need to connect these two pieces. Again, just being careful that I connect them in a way that ensures that the graph still passes the vertical line test. My drawing is a little bit sloppy here, but I think you can see where I'm going with this. That squiggle shouldn't be there, but what else? We wanted discontinuity at -5. Something weird is happening at -5. I should really have like an empty circle or something here. It's kind of bad form to just have a line just kind of end at that point. These two pieces should be connected. There's no reason for those to be disconnected. And then I think we can connect these two like this. Right, there we go. Again, it's all about just connecting them in a way that doesn't violate the vertical line test. Like if I did something like this, that would be bad, right? That would very clearly violate the vertical line test. So I just need to connect them kind of as simply as I can. And I think that does it. So that is certainly one possible answer to this problem. There's many other ways of doing it. So, you know, your graph may not look like mine, doesn't mean it's wrong. But yeah, so those are pretty tricky. So hopefully you were able to follow some of that. Okay, so let's move on to some new stuff. Like I said, today we're really going to focus on evaluating limits algebraically. And what do I mean by that? So let's start with an example. Suppose you're given this function right here, f of x equals x squared minus 9 over x minus 3. That's an example of something called a rational function. A rational function is basically just a fraction, pretty much. You can see it's a fraction with variables in the numerator and denominator. That's pretty much what a rational function is. I've drawn a portion of the graph of this function over here to the right. And as you can see from the graph, there's actually a hole at x equals 3. You can see the hole right here. And so it's and so there's kind of a hole. And suppose that I asked you, what is the limit as x approaches 3 of this function? Okay, suppose I asked you, what is the limit as x approaches 3? Well, if you look at the graph, it's very clear that the two-handed limit is defined because the left and right hand limits approach the same number, and they both approach 6, right? So the two-handed limit is 6. That's pretty clear from the graph. But why in the world is the limit equal to 6 from the perspective of the formula? Here's what I mean. Like, if we have a graph, it's pretty obvious that the two-handed limit is 6. But what if we don't have a graph, right? What if we didn't have a graph? How could we figure out the value of this limit without graphing the function? That's really what today's lesson is all about, evaluating limits, you know, like this, taking the limit as x approaches 3 of this function, but without looking at the graph, okay? And you might wonder why that's important. The truth is that this graph, like we said, has a hole at x equals 3. There's like a little hole in the graph. I had to insert that little hole manually. If you actually graph this function in Desmos, Desmos will not plot the hole. There's kind of a complicated reason for that. Basically, it's because the hole is technically like infinitely small. It's like one point is missing from the graph. So it doesn't show up because it's too small. So, you know, this finding limits algebraically is really important because if you graph a function like this guy here on your calculator, it really will not be evident that there's a hole in the graph at all. So anyway, so how do we find limits like these guys without looking at the graphs? In other words, how do we find limits just by looking at the formula for a function and not the graph? That's the question for today. How do we do it? So there's kind of not a lot to it. Here's the idea. Let's say that you want to find the limit as x approaches c of some function f, and you've got a formula for f. You don't have the graph, but you have a formula. How do you find that limit? The first step is that you plug the number c directly into the function. Okay, so whatever x is approaching, you just try plugging that number into the function, okay? And there's really just like a few things that can happen when you do this. If you get a number, that is, if you get like a well-defined, ordinary, old-fashioned number like 2 or -5 or 0 or a half or square root of 3, if you get a number, that's the value of the limit and you're done. Okay, so if you plug c into the function and you get 7, then the value of the limit is 7. That's it. There's nothing more to it. Most of the time, that's not what will happen. Most of the time, instead, you'll get something like 0/0. Okay, if you get the expression 0/0, what that means is that you have to rewrite your function. It means you have to simplify your function. You might be tempted to say that maybe 0/0 means 1, or maybe it means 0. It actually doesn't. 0/0 is an undefined expression. It's a meaningless expression. 0/0 could mean 0, or it could mean 1, or it could mean infinity, or it could mean 12. It really has no meaning at all. It has as much mathematical meaning as like a happy face. It just doesn't have any meaning. So, the game plan here for evaluating limits algebraically is you take the value c, you plug it into the function, and you see what you get. If you get a regular number like 7, that's the value of the limit. There's nothing else to do for the problem. You write down 7, you circle it, and you move on. Most of the time, that won't happen. Most of the time, you'll get 0/0, which means that you have to simplify your function somehow. You have to rewrite your function and then try plugging the number in again. Okay, that's what it means. So let's see an example of this. Oh, by the way, going back to this example, I won't do it all the way out, but remember we looked at the limit as x approaches 3 of this function here. If you actually plug 3 into this function, you'd get 3 squared minus 9. That's like 9 minus 9, which is 0. And then if you plug 3 into the bottom, you get 3 minus 3, which is also 0. If you plugged 3 into this function, you'd get 0/0, right? So yeah, usually when you get 0/0, it means there's a hole of some kind in the graph. Okay, so let's do some examples. So here's our very first example. Let's try to evaluate the limit as x approaches 6 of this function right here, x plus 4 over x minus 4. So what's the procedure? The procedure is that you just plug 6 into the function, like you replace the x's with 6's, and you see what happens, okay? So if you do, you have 6 plus 4 over 6 minus 4, which is 10 over 2, which is equal to 5. Is that a number? Yeah, that's a number, right? So because we got just an ordinary number, that's the value of the limit. So the value of this limit is 5. There's nothing else to do. As a matter of fact, if you look at the graph of this function and you look at what's happening at 6, the truth is nothing interesting is happening at 6 at all. It's just a continuous curve. I highlighted the point, with this black dot just to emphasize it for you, but really like nothing interesting is happening at 6 at all. You plug in 6, you get 5, that's the end of the story. Nothing weird is happening. There's no hole, there's no discontinuity or anything like that. Okay, fine. So that's an easy problem. Now let's try one that's a little bit more complicated. Let's try the limit as x approaches 2 of this function right here. Okay, now the first thing that you should try, like I said, is you got to plug the number in. So take 2 and plug it into this function and see what you get. All right. So if you plug 2, that's weird. It looks like there's a typo. It looks like it says plug -2, but that's not what we're plugging in. We're plugging in 2. So we're going to plug 2 into this function. And when you do, you have 2 squared plus 2 minus 6 over 2 squared plus 3 times 2 minus 10. If you do the arithmetic, you get 0/0. So what does that mean? That means that we've got to simplify our function. We've got to go back to our function right here. We've got to simplify it somehow. We've got to like rewrite it, do something with it, rearrange it, simplify, and then try again. Now, the question is, when I say rewrite or simplify, what do I mean? Usually it just means simplify. Usually we just need to simplify the function. You might wonder, how do you simplify a function like this? There's a few different things that can happen, and I'm going to give you kind of like a list of the different things that can happen. But one of the most common ways that you need to simplify, and that's what's going on here, is that you need to factor the numerator and denominator and then cancel common factors. Okay, so if you look, the top and bottom of this fraction, you know, they're both quadratics, right? Like they're both degree 2 polynomials, and you can factor each one of them. So let's factor them. Okay, so x squared plus x minus 6. Let's think about that. So how does that factor? You need a pair of numbers that multiply to -6 and add up to 1, right? The coefficient on this term. So pair of numbers that multiply to -6 and add up to 1, that would be 3 and -2. So the numerator factors as x plus 3 times x minus 2. If you've got a different method of factoring, that's fine. Like whatever method you want to use. Denominator is the same story. We need a pair of numbers that multiply to -10 and add up to 3. The pair of numbers that do that is 5 and -2, right? Multiply to -10 and add up to 3. So the denominator factors as x plus 3 times x minus 2. Now, if you look at this expression, you'll notice there's a factor of x minus 2 on the top and a factor of x minus 2 on the bottom. And that means that it can be canceled. We can cancel that common factor of x minus 2 from the top and the bottom. So I cross out that factor of x minus 2 on the top and the bottom, and my function simplifies as just x plus 3 over x plus 5. So this guy right here, the x plus 3 over x plus 5, that is the simplified version of my original function. And now that we've simplified it, we try plugging into again, right? We try plugging 2 into this new simplified version of the function, and hopefully this time we get a number, okay? So if you plug 2 into this function, of course you get 2 plus 3 over 2 plus 5, which is 5/7. 5/7 is a perfectly ordinary number, nothing wrong with it at all. And because 5/7 is a number, that's the value of the limit. So this limit is 5/7. So what happened in this example? Well, we plugged in 2, right? We plug in this number, and we got 0 over 0, which tells us that we need to simplify the function. So I simplified the function by factoring and canceling common factors. And then after you're done simplifying, you try plugging the number in again. And hopefully the second time around, you get a reasonable actual number. And we did. We got 5/7. So that's the value of the limit. So that, broadly speaking, that's the process of evaluating limits algebraically. You just take the number, you plug it in. If you get a regular number, that's the value of the limit. If you get 0 over 0, then you need to simplify and try again. Now, the tricky part is basically in knowing how to simplify the expression, okay? And, oh, and by the way, just to wrap up this problem, the graph looks like this. As you can see, there's a little hole sitting at 2. 0 over 0, if you get 0 over 0, that usually means that you have a hole in the graph. Okay, so simplifying and rewriting functions, like, what does that mean? I mean, in this particular example, it meant factoring the top and bottom and canceling common factors. But in other problems, it will mean different things. So what are the different kinds of simplification that you need to be thinking about? What are they? So there's really just a handful of them. And I've got a list of them right here. Okay, here are the different things that you'll have to do in order to, simplify or rewrite your functions. This is the first one. It's the one that we just did, right? Factor everything and cancel common factors. This is really common. Really commonly, this is what you're supposed to do. If you see square roots, in other words, if roots are involved, if you see square roots floating around in the expression, then what you'll have to do is multiply top and bottom of the fraction by the conjugate of the root expression. This is something that I'm going to go into more detail later, but this is kind of a tricky one. This is the one that students have a lot of trouble with. You might have to simplify complex fractions. If you remember, a complex fraction is like, it's when you have a fraction within a fraction. Like I'm sure that we have some down here. Like, for example, this guy right here. That's a complex fraction. You got fractions within fractions. If you have an expression like that, you'll have to simplify the complex fraction. And simplifying complex fractions basically means you make the numerator of the entire expression into a single fraction, you make the denominator into a single fraction, and then you like use keep it, change it, flip it. It's kind of a complicated story. I'll say that if you've never seen this before, like if you're coming from Trigasis, I don't think that you've seen this before. And I'd probably recommend that maybe you skip problems like this, like complex fractions. Probably not necessary. I think if you're coming from Trigasis, you may also want to skip the conjugate root problems, so like the problems involving roots, like this guy right here. But if you're, because I don't think that you'll do those in foundations of calculus, but you will do them in AB Calc. So if you're coming from pre-calc honors, if you're taking AB Calc next year, then you should do those. So and then what else? So if you see something that can be multiplied out, like an x+3 quantity squared, then you should multiply stuff out and collect like terms, right? Like x+3 quantity squared should be rewritten as x+3 times x+3. You should multiply everything out, like collect the like terms, and then something nice hopefully will happen. Okay, and then finally, if there are multiple fractions, try combining them, like try combining the fractions. I'll show you. So in a minute, so what I'm going to do, I'm going to go over in detail this thing that I mentioned here. Like when you see roots, try multiplying top and bottom by the conjugate. I'm going to go through an example like that in detail. And then I'm going to quickly look through a bunch of these and just sort of tell you like which simplification type you should be thinking about, just to give you a little bit of a ladder for these exercises. So let's have a look at this example here. It's a limit as x approaches 1 of root x minus 1 over x minus 1. So the very first thing you should always do in these problems is plug in the number. So just take 1 and plug it into this function. I promise that if you do that, you're going to get 0 over 0. If you plug in 1, you get 0 over 0, which tells you that you have to simplify. Okay, so we've got to simplify. How do you simplify? Because of the root expression right here, most likely what we have to do is something called multiplying top and bottom by the conjugate. Okay, by the conjugate of the root expression. Here's what I mean. The root expression in this case is root x minus 1. That means you're going to multiply top and bottom by root x plus 1. And the conjugate, this is a word you may have heard before. The conjugate of a minus b is a plus b. You just change the minus to a plus, okay? So the conjugate of this guy is actually just root x plus 1. So you're going to multiply top and bottom of the fraction by root x plus 1. So let's see how that goes. So here's the original expression, right? And now I'm going to multiply the numerator and the denominator by the conjugate, by root x plus 1. Okay, now notice I've put everything in parentheses. That means like we have to multiply everything out, like we have to FOIL. It's kind of a pain. So let's see how this goes. So you have to distribute, right? So root x times root x is just x, okay? Root x times 1 is just root x, okay? Negative 1 times root x is negative root x already. And then finally, negative 1 times positive 1 is negative 1. Okay, so I've multiplied everything out, I've FOILed, okay? Now, you'll notice that I've multiplied everything out in the numerator, right? That gives me this, but notice that I didn't multiply anything out in the denominator. I just left it alone, like I just left it in factored form. We're gonna see why I did that in just a moment. So what I want you to notice though, is that the numerator can be simplified. Do you see what can be done? See the root x minus the root x? They cancel, right? These two middle terms cancel. And that just leaves you with x minus 1. And now look at this expression here. Do you see what can be done? You've got a factor of x minus 1 on the top and a factor of x minus 1 on the bottom. They can be canceled. That's a common factor. If you cancel the x minus 1 from the top and the bottom, you're left with just 1 on top and then the root x plus 1 on the bottom. Like cancel this, cancel that, and we're just left with the 1 over root x plus 1. So this guy here is the simplified version of our function. And now we go back and we ask, what were we taking the limit? We were taking the limit as x approaches 1. So now try plugging 1 into the new simplified version of the function. If you do that, you're going to get 1 over square root of 1 plus 1, which is 1/2. So you'll get 1/2, which is a regular old-fashioned number. So that's the value of the limit. It's 1/2. So that's an example of having to multiply top and bottom by the conjugate. It's what you should do pretty much anytime you see a root inside the function. A couple of comments on this. So first of all, you multiply top and bottom by the conjugate of the root expression. In this particular problem, the root expression appeared in the numerator. So I multiply top and bottom by the conjugate of the numerator. But the root expression can appear on the bottom as well. So you multiply top and bottom by the conjugate of the root expression, wherever the root expression appears. Sometimes it'll be up top, sometimes it'll be down below, but you always multiply top and bottom by the conjugate of the root expression. The other comment that I want to make is that remember how when you FOILed this guy out here, when we multiplied these terms out and we got these two middle terms and these two middle terms canceled? That's not an accident. That will happen every single time you do this. Okay, the idea is that when you take an expression and you multiply by its conjugate, the two middle terms will go away. If your algebra is really solid, then you can see why this is true. What you're doing is you're multiplying by, you're multiplying a sum and a difference. It's like a minus b times a plus b. And that always multiplies out as a squared minus b squared. So it's like difference of two squares, but in reverse. And remember how I said, so you should always expect cancellation of the middle terms, right? When you have the expression times its conjugate, the middle two terms should cancel out. And the other final thing I want to say about this is, remember how I didn't multiply out this guy down below? Always do that. You should only multiply out the expression times its conjugate. Like here's the root expression, here's its conjugate. Okay, so you have an expression times its conjugate that you want to multiply out, but the other expression you just want to leave alone because we left the denominator in factored form, and because we did that, it was clear at this point that this guy here canceled with this guy here. If we hadn't left the denominator in factored form, then it wouldn't have been clear. So anyway, as I said, if you're going into AB, you should know this kind of process. If you're going into foundations, then I wouldn't worry. I would skip the problems involving roots, and I would skip the problems involving complex fractions, right? So I would skip problems like this one here, number 8. That's a root problem, and I would skip number 3 right here, and that's a complex fraction problem. But if you're going into AB, then you should do those. So very quickly, oh, actually, we give you hints about how to do a lot of these, right? So read the hints. They really tell you what you should be doing. Number 4, it says you're going to need to factor the numerator. You might be wondering what kind of factoring you can do there. You can pull out a common factor of x. Do you guys see that? It would just be, you can plot an x, and it'd be x times, in parentheses, x plus 5, and then the x's will cancel. So yeah, and then likewise here with number 5, the denominator, there's a common factor of 5 that you can pull out. So make sure you're aware of that. Okay, so give those a shot, and we'll go over a few of them at the beginning of next class. Yeah. Okay. Good luck, guys.